Right, I suppose a little bit of my background. I work at CSIRO on the Atlas of Living Australia project. We're responsible for mapping biological and environmental data on a map, so I'm in the geospatial team. How many people in the audience have used OpenStreetMap? Okay, how many people know what's happening behind the scenes? Righto, so this presentation will hopefully give you a glimpse into what's happening behind the scenes with OpenStreetMap. For me, OpenStreetMap was the defining project that sort of, when I started to take notice of open source mapping software and open source mapping data, it was sort of a massive sort of explosion of user-generated content for the web. So I'll just try and zoom into our country, just for a tick, just to show those who haven't seen this before. We'll zoom in a little bit. And I'll explain a little bit about what's going on behind the scenes. So I'm not 100% sure when the OpenStreetMap project actually started. I know it was probably about 4 or 5 years ago. But when I first saw it, I sort of looked at local content and I thought, well, this has a long way to go. Like, I looked at it and compared it to Google Maps. A few years later, I looked at it again and I was blown away. Like, suddenly there's street level data. Like, so we can, as you can see here, we can see names of streets, we can see parks, we can see cycle paths, roads. Yeah. But how's this getting to us? So what's actually what are the technical sort of layers that go into this? So we've got a web application with a gazetteer name search here. We've got openlayers over here, which is a JavaScript framework that's used to talk to a map server and render layers on the map. There's some widgets, some JavaScript widgets here to zoom in and out of the map. You can see a layer switcher over to the right where you can switch the actual data source that's being overlaid on the map. Okay. If we have a look at Firebug and we move around the map, we can see all of these tiles are being requested. So it's like a puzzle. So OpenLayers is actually saying, I want to render this part of the map, and it requests the tiles from a map server. The map server is responsible for actually generating that image and sending it back to the client. And it gives you that sort of nice Google Maps scrollability, because it will render a few maps around the user portal, so it feels like it's a smooth process. But what's happening behind the scenes there? Like, what does the map server actually do? Where does this data come from? Well, this is where geospatial databases come into the mix. So postgis is the most prominent open source spatial database, and there's a map server that sits on top of that. So the two most common implementations are map server and geoserver. Today I'll be focusing on geoserver because that's what we use on the project that I'm currently involved with and I'm most familiar with it. So in a nutshell, this is what I'm going to cover today. I'm going to talk a little about web mapping standards, the OGC standards, the architecture of GIS, spatial databases, spatial clients, geospatial services, where you can get some nice open data to push into your map server, and I'll do a little demonstration of the project that I'm involved with, the Atlas of Living Australia. So the Open Geospatial Consortium, OGC, are sort of the IEEE of the spatial world. They define a set of standards for data interoperability of spatial data. So spatial data consists of two main types. You've got vector data and raster data. The three main services that I'll be talking about today, or I'll be covering today, WMS, Web Mapping Service, WFS, the Web Feature Service, and WCS, the Web Coverage Service. These are the three most common services defined by OGC. So I'll just have a chat about each one in turn. WMS is when a client, such as openlayers, requests for a particular bounding box, I'd like to render this map. The images are then generated server-side and possibly cached, or possibly come out of a cache, and then sent back down to the client as an image, typically a PNG. WFS, the request says, I want all features for this particular bounding box, and the actual raw data gets sent back to the client and rendered client-side. So the lines, the points all get rendered in the client. So the processing gets pushed from the server to the client. WCS is used to request gridded data, or raster data with specific criteria. So you can say, I want information from this heat layer between the temperatures of 20 and 25 degrees Celsius, and it will return back a cut down version of that gridded data. I don't have a lot of experience using WCS. In fact, we disable it we actually disable WFS as well, and we just present a WMS layer to our data. And I don't know a lot of clients that actually use WCS presently. So uDig, which is a common GIS client, I couldn't see WCS as a supported protocol. Feel free to interrupt me if I'm wrong. That actually goes for the entire talk. If you have questions, feel free to ask me. I want it to be sort of an organic process, and we can all learn together. Because spatial information systems is quite a deep topic. There's a lot of ground to cover, and a lot of room for confusion. So by the end of this presentation, I'd like to show you some of the things that I've learnt in the last 12 months, and hopefully make it easier for you and give you some good URLs and some good books that you can go off and read and do these things yourself. Earlier in the week, someone pointed me in an XKCD comic, and given we're a room full of geeks and we all know XKCD by number, can anyone in the audience tell me which one that is? So I wanted to talk about map projections a little bit, and they're probably it's one of the more confusing sort of sides of mapping. The world isn't a perfect sphere. It's actually quite bumpy, and when you're trying to project a three-dimensional shape to a two-dimensional shape, you're going to get distortion at some point. So over the years, like this predates WebGIS and computers pretty much. It's quite ancient. People have come up with ways of projecting spatial data onto a two-dimensional surface to try and limit those distortions, or at least make one particular area on the Earth more accurate. So I thought this was an excellent comic. He actually put a bit of effort into it. So as you can see, well worth having a read of, and it's actually very, very funny. But it gives you an idea of, this is probably my favourite. It freaks you out to realise that everyone around you has a skeleton inside them. Yeah, so, but basically we start off with the Mercator projection, which is just a standard lat long. And we can see here you get distortion at the poles, and it's not really an accurate representation, but it is the simplest. So a lot of people just sort of stick with that type of projection. And then as we move on, they come up with different ways to sort of lay the Earth out so that at particular points, so there's the Winkle triple that the National Geographic uses. So for that particular region on the Earth, it provides a better perspective of that part of the Earth. Oftentimes it's described like when you're trying to map the Earth, take an orange and you wrap a piece of paper around it and then roll it back out again, and you get something that looks like this, sort of, or you take a peel off an orange, and you get a projection that looks similar to that one. And then you just get really, really wacky ones like the Waterman butterfly. So GIS, open source GIS services have to understand all of these different projections. One interesting one that I was reading about recently was the US military. They don't use any of these. They actually split the Earth up into grids. And each grid has, I think, eastings and northings associated with it. So when they go into a theatre of war, they have very accurate maps for that one part of the world. So, yeah, so you need a way to be able to represent that in these, or interoperate with those sorts of projections or those systems. To give you an idea of some of the information that's associated with the projection, you need to have area, shape, direction, distance, scale. So you could be talking about degrees, metres, kilometres, lat long. The shape is quite important. They often talk about spheroid or ellipsoids or spheroids and geoids. So there's like a magnetic reading of the surface of the world. So all of these are algorithms that are used to sort of plot points on the map. It's really quite a tough one to explain, and I've heard it explained to me several times. I highly encourage people to read up more about it and do a lightning talk and correct me or shout out if you can think of a better way to describe it. But this is the bit that really. But at the end of the day, the GIS tools do a lot of these transformations for you. So but keep in mind you are making trade-offs. So Jody described it as. Every time you get a data set, make sure you work off the original one, because every time you convert it into another one, so say WGS84 or EPSG 4326, which is a standard latitude and longitude, it distorts the map. And so every time you transform it, it distorts it and it becomes more inaccurate. Similarly, if you're working on regionalised data, say GDA 94 for New South Wales, which is a common one that Geoscience Australia use, you might want to consider storing everything in that format, and operate off that raw data format. So I've just thrown a few buzzwords out there. I've probably confused everyone already. If you are doing web mapping, 4326 is pretty much the standard. Latitude, longitude, you'll see it everywhere. If you're going to remember any of these codes, that's probably the one worth remembering today. So that's latitude, longitude, or longitude, latitude. The terminology is actually it's actually reversed in this field, which it just confuses a little bit more. And then there's EPSG 900913, which is the same sort of it's the same projection, longitude, latitude, but it's in meters rather than kilometers. And this is the one that Google used, so it's easy to remember because it's Google in numbers. And it's the one that you have to convert to when using Google Maps API or even openlayers. And there's another one I'm just throwing out there. This is one that I've come across, which is GDA 94, which is New South Wales Lambert projection, which seems to be used a fair bit for our region. So you may come across that if you have a data set. Spatial formats. So these are some of the common formats that I've seen data presented. Esri shapefile is by far the industry standard for spatial data industry. Esri itself being a commercial company, so that they have been the market leader in this space for many years. WKT, well-known text, is a textual representation of a shape. This is vector-based data. So wickets are used quite commonly in postgis for input and output. This is how you get spatial data into a system. KML, which I think used to be GeoML, or there was some other standard, but it's the keyhole markup language which Google acquired with Google Maps. Two others used more for spatial interchange, GeoJSON and GeoRSS. And so those ones that I've just mentioned, they all deal with vector-based data. So points, polygons and lines, they're the three sort of data types that we deal with. And then finally we've got raster-based formats. A common one is GeoTIFF, Esri Grid or ASCII Grid. There's another one called BIL, which I've seen available. And so rasters are essentially, it's a grid of pixels, and there's a there's a scale associated with that, and they also have a projection associated with it. So when you get a GeoTIFF, commonly you'll open it up and you'll just see a grayscale image, and it'll look really boring, and you go, where are all the nice colours? Because you're used to seeing heat maps or temperature maps or gridded data in a colour form. Well, I'll get to that a little bit later. But it can also be used to represent multi-dimensional data as well. So there can be a lot of data embedded into a GeoTIFF file that you just can't see by opening it up in an image editor. So it's it's an interesting format. This is another format that I've come across in my travels, NetCDF. It's used quite extensively in the scientific community. It's used to store multi-dimensional spatial data, specifically if you're dealing with time or temporal data and depth-based data. OpenDAP and Threads are two open source implementations that support NetCDF. Threads itself supports WMS, that should be, not WMC, and WCS services. And there is a client called Panoply, which I think I've got running here. So here we can see some NetCDF data rendered, and here we can muck around with projections, so we can reproject to all of those sort of wacky projections that we saw in that XKCD comic. So yeah, they get quite odd. The Winkle triple match here. Okay, I'm just going to talk about what a spatial server actually is. I mentioned GeoServer and map server earlier. So an OGC compliant map server will support those three main protocols that I described before. WMS, which is the server-side image rendering, WFS, which sends the features back to the client, and WCS that allows you to narrow down on gridded or raster data. It supports a filter language called CQL, not SQL, CQL. It looks very similar to SQL. It supports styling, which I'll come to. That's sort of the magic sauce for colorizing the spatial data and making it look pretty. Legend generation, and supports the on-click event. So when you send the image back down to the client and they select a point on that map, you expect an event to occur. Some data to be sent back to the client. So to say you click on a map of Australia and you click on New South Wales, you want it to send information back about that particular feature that they've clicked on. So it has to support that type of event. They also support a get capabilities request. So you can connect to a GeoServer or a map server implementation and say, hey, what kind of spatial data do you actually have, and what formats or what protocols do you support, and what projections do you support? And get capabilities will actually tell clients, it's like metadata about the map server. So I'll do a quick demo of GeoServer, give you a quick run through of that. So GeoServer is just it's a Java web application. So I've got it running locally on my Mac. It's just we can see it running there. Just runs off port 8080. So what do we got? We've got layers, stores, and workspaces in the middle there. Workspaces and stores are workspace is a way to sort of segregate a project. So Atlas of Living Australia would be a workspace. Stores allow you to connect to back-end data stores, so it could be a PostGIS database or a GeoTIFF file or a shape file on the file system. And a layer is it's a rendering of that. It's saying, I want to use this GeoTIFF file and I want to apply, I didn't mention styles. Over here we have the styles. Here we define what's called an SLD. It's sort of like a style sheet for maps. And that allows you to define what colours relate to the values in a raster. So say you have a raster that has temperatures over a grid. You can say, I want it to be red between 20 and 30 degrees, or yellow between 10 and 20, or blue to be between 0 and 10. It's just an XML definition. And when you define your layer, you define a style, and away you go. There's also a thing called Geo Web Cache, which comes with GeoServer. So as you could imagine, once you have layers with a lot of features, in our case we have 20 million species occurrence records. You could imagine that if you request a tile with 20,000 points in it, it could be quite expensive server-side to actually generate that image. So Geo Web Cache is used to cache the tiles, pre-cache the tiles, so that you don't have to go through that ordeal every time a client requests those tiles. So the reason why Google Maps is so fast is they pre-cache tiles en masse in the cloud. So that's what gives them that performance. You can pre-seed your tiles as well. GeoServer has a REST API, so you can write sysadmin scripts to actually automate a lot of this process. You can automate the data, the actual creation of the layers, the creation of the stores, creation of the styles, and also pre-seed the cache. So you can kick it off and it can actually automate a lot of this. So let's have a look at a layer. And log in. We can see here the icons actually represent the type of layer that GeoServer has in the system. A grid is a grid file or a raster file. A polygon is a polygon, line, point. So, and what we can do is we can actually do a layer preview and actually take a look at each of these layers. So these are pretty much the defaults. So if you install GeoServer, you'll see a whole heap of pre-built examples just to demonstrate the capabilities of the product. And if we drop this down to all formats, we can see that these grid files support WMS only. So if it was a shapefile or a vector layer, we would see the WFS side of things populated as well. So you'd actually be able to request the features directly. If we go JPEG, there we go. So that's and you can see up here in the URL, this is the actual constructed WMS request here. So it's asking an image with these dimensions in 4326 format, EPSG 4326, so it's just standard latitude, longitude, latitude. It's requesting a JPEG, and here is the bounding box over here. So that's the entire Earth. So minus 180 degrees, minus 90 degrees, 180 degrees, 90 degrees. Styles, it's just using the default style associated with that layer. You can actually override styles if you want. You can inject your own style to a WMS server and get things rendering in a different way. We could also put in a CQL filter at this point as well to narrow the data down. We'll pick a raster one as well. So we can see here that the WFS is features are supported as well. And this kind of shows who attended the GeoTools workshop in the mini-conf. So a lot of what drives GeoServer and also uDig is GeoTools. And so a lot of these formats will look familiar because it's all the stuff that GeoTools supports. So CSV export, GeoJSON, GeoRSS. So it's that library that's driving this product. And you can see here that you can actually download a shapefile from using WFS, so you can get access to the raw data again. And that's why we had to sort of disable WFS, because we had licensing issues associated with the data. We couldn't redistribute it, or we were limited in how we could redistribute the mapping product. So that's something to keep in mind. If you are opening up your spatial data, consider switching off raw access to your data, just in case, or at least check your licensing in terms of use when you're doing that. Again, let's go. Let's do a. You can see here that there's an open layers option as well. So if we select the open layers view, it'll render it just like we saw in OpenStreetMap. So we have the slider here to zoom in and out, the pan operation. It's pretty boring. It looks really boring, but You can actually add your own base layers to that if you want. So you can actually say, I want to use Google Maps as a base layer within openlayers. You could choose Yahoo or even OpenStreetMap as a base layer. It doesn't have to run off your server. It's all using WMS, so it's a web-based protocol. There's some more options here, so you can actually apply a CQL filter to it. Or if it supports get feature requests. Restricted. Moving on, one more is some point-based data. So these are just points plotted on the map. Again, if you had a base map, it would make a little bit more sense, but you get the idea. Cool. Okay, thick clients. I'll just talk briefly about 3 of the main ones that I'm familiar with. uDig, I think, is the best open source GIS client out there that runs on Linux. There's a few ones that run on Windows as well, which I don't actually know off the top of my head. They do look promising, but uDig's written in Java, uses GeoTools. Chances are, if you can render the layers in uDig, it'll work in GeoServer, so it's a good way of taking a look at spatial information before you invest the time to put it into PostGIS and put it into GeoServer. Worldwind, which is it's an open source clone of, I don't know if it's a clone, but it looks like Google Earth essentially, and then of course there's Google Earth. Yeah, so just thought I'd better mention Google Earth. I'll just give you a quick demo of uDig just so you see what it looks like. So this is uDig. I've loaded up a few polygon layers here from shapefiles. These are sort of quarantine zones, like it's work-related data, but it sort of gives you an idea of what the UI looks like. It allows you to zoom in, zoom out, pan around, get feature info. So if we go, here's this one here, and we click on a polygon, it'll actually return information that's associated with that record. So what I should say, a shapefile has a series of key value pairs that represent, you have a polygon or a geometry, and then you have additional attributes associated with that, and you can have as many as you want. It's like a table in a database, and these attributes. So if we look down this list here, can be used to narrow down that CQL filter. So you can say where feature type equals FFEZ, and you'll only get polygons that are part of the fruit fly exclusion zone. So it's, when I say it's a bit like SQL, it's a very basic sort of version. Like you don't have any joins or anything like that. It's like a one table kind of filter. But it does support things like spatial filters. So you can say, give me all spatial features within this particular geometry, or that intersect with this geometry, or within 10 kilometres of this particular point. So there's a series of spatial operators you can use to sort of narrow down on specific spatial data. And uDig's good because it doesn't just support. It's actually a WMS client as well, so you can connect to a WMS server and use the get capabilities, find out what map layers are on that server and render them. So you can actually overlay local data and also remote data and mash it up. And so it's quite a powerful utility in that regard. There's a lot of other open source projects that have been spawned from this. So a lot of people have taken uDig, modified it, tweaked it for a client, and then they've got their own GIS capability, or client-side GIS capability. Yeah, and it's not really it's not limited to vector-based data. It also supports all of the GeoTIFF formats. So I'll just load up I'll load up one just to demonstrate. Import, and this will give you an idea of some of the formats that you can actually import. So it's quite a wide variety of data sources that it can connect to. It can connect directly to your PostGIS instance and render data out of your PostGIS tables. I'm just going to go for a file. So I've downloaded some data from Natural Earth Data, which is a nice provider of free maps. This is just a base layer. That looks nice. Okay, and then to overlay it, you can just drag and drop it out of your catalogue and into your current map. So it sort of has this concept of projects, layers, and maps. So you'll kick off a project in uDig, and then you'll create a map, and then a map has layers. So that's sort of the terminology that uDig uses. But we can see here we've overlaid a GeoTIFF image. This one actually has colour information embedded into it, so it's quite a pretty base map to use. And we can see here that the polygonal data as layers is overlaid over that map. And we can zoom in and pan around, and as you can see, like this particular image, it's quite large. Like it's quite a large download because the resolution is quite nice. So, all right. Web-based clients, there isn't really much in that space. You're really limited to openlayers, like for the web. I say that, but things might have moved on a little bit since when I started. Back when I started, openlayers was sort of the way of doing online WMS, building a WMS client. There might be more movement in that space, there might be new capabilities out there, but it's a very rich JavaScript framework for building maps, and it's fully OGC compliant. But there's also a hack as well. There is a way to get Google Maps to work with WMS. I've written a blog post on how to do that. You can come see me after the presentation if you find yourself interested and you want to integrate a WMS server with your Google-based map application. It's a little bit of a hack, but it seems to do the trick. And it was good at the time because OpenLayers was playing catch up in terms of portable devices, so supporting the touch-based interface. So Google Maps was really the best portable mapping client, web-based mapping client. There was just no way to get around it. And Google's actually moving quite heavily into this realm of fusion tables and your data in the cloud, and it's a really big push from them at the moment. I'm not an expert in what they're offering, but there is definitely movement in that space. Mention that. Spatial databases. I've mentioned PostGIS. PostGIS is basically a package for PostgreSQL. It installs a bunch of functions and a couple of tables. I'll do a little bit of a demonstration later on about that. But it's nothing too scary about it. There's a few C libraries that are required to do the geometric projection mathematic sort of operations that are needed. But it's quite easy to install. A lot of the common vendors will ship PostGIS nowadays. I think Susie do. OpenSUSE. Yeah. Okay. There's also a commercial Postgres, or a semi-commercial Postgres offering from Enterprise DB, which you may be familiar with, and that has an optional PostGIS package, so it makes it really simple to get up and running with PostGIS. And commercial offerings, I should mention that. There is Oracle Spatial, Microsoft SQL Server that have geospatial database offerings as well. I don't have a lot of experience with those, but a lot of the open source tools that I'm going to talk about further in this presentation will interoperate with PostGIS and Oracle Spatial, and I think perhaps Microsoft as well. So you're not limited to an open source database, or you might be in an environment where you have to hook into a commercial product. So Jody Garnett presented an excellent workshop earlier in the week on GeoTools, which is the Java Geospatial API, which actually drives GeoServer and uDig. I'm not going to say too much more about that at this point in time because obviously Jody's covered that in quite a lot of detail, but you'll get a feel for what GeoTools is capable of as I demonstrate the product a little bit further. So, OGR is a simple feature library, so this is more low-level tools that you use for working with geospatial data. So this is used to manipulate and work with vector-based data. So changing, if you want to alter a projection of a shapefile, you would consider using OGR to actually perform that transformation. Converting to different types. So if you've got a shapefile and you want to convert it into a wicket or another vector-based spatial data format, you would use OGR or the OGR suite. And also merging shapefiles together. This is another. I've used this to merge multiple shapefiles from multiple sources into one. So I have a single layer consisting of multiple shapefiles. So there's a couple of commands there: OGR info, OGR to OGR. And then there's gdal, which is the Geospatial Data Abstraction Library. OGR and gdal are typically packaged together. So you apt-get install it, and you pretty much get the whole kit and caboodle. So this is used to manipulate and work with raster spatial data, changing projection, converting to different types, changing the grid size. So say you've got a 0.01 degree grid size and you want to decrease the resolution of that data, you would consider using, or you would use these tools to actually mess with that and transform it. There's a few others there. gdal rasterize, which you can use to convert a shapefile to a raster. So you can actually go from a polygon to a raster, and it's called burning in. So you pick a particular you pick an attribute and you burn in the shape into it, and you can actually burn in different levels into the raster. And then there's gdal polygonize, which you can actually convert a raster into a shapefile. So say you have different crop types, so you have a map of Australia and you've got a grid and you see all the different crop types, you can actually create shapefiles based on those attributes. So it's another technique that we use for sort of in our spatial data analysis, converting between the two different formats, and they are very different formats to work with. I'll talk a little bit now about geocoding. I've worked on on a prior project where we had a requirement. We had a customer database with a series of addresses in there, and we had a requirement to produce to get lat longs for street addresses. Sounds like a really basic problem, doesn't it? Just use the Google API to do that. But we didn't really want to subscribe to the terms of use. We didn't want to make that data publicly available, which Google make you do. So we looked at other offerings from Yahoo and Microsoft, and we sort of chased our tail for quite a while, and then came across the OpenStreetMap project. And the OpenStreetMap project has a thing called nominatum.openstreetmap.org, which is a geocoding server for OpenStreetMap data. So all of the OpenStreetMap data is in a PostGIS database, and there's been some indexes applied to the name, the street names, the suburbs, all of the textual information related to an address. And you can say 10 Walker Crescent, Jerrabomberra, and it will return a latitude, longitude. It's not perfect. I think even the 10, it'll ignore that. It'll just give you the street. So it doesn't do street level geocoding at present, or it didn't a few years ago when I played with it. But it's your data. You've got the latitude, longitude, and you can store it behind your firewall, and it doesn't cost you $15,000 in Google licensing. But it can take a long time because this is running off someone's server in their basement, right? So OpenStreetMap doesn't have a lot of money. They don't run in massive clouds like Google does. So we were getting pretty poor performance, and we had a lot of addresses to geocode. So you can actually download the entire OpenStreetMap data set. Every single street, park, everything. Everything you saw on the very first slide, you can have locally in PostGIS, and you can index it and do your own geocode lookups. So we did that. So we downloaded the world. It was 8 gigabytes in size, extracted to 250 gigabytes, quite large, and we kicked it off. Put it into PostGIS. It took about a day, 24 hours or so, to actually insert into the database. And then it took about another week or so to actually index, because it had to index all of that textual data to be able to do the geocoding. Followed a few online instructions. If you go to nominatum.openstreetmap.org, I'll send you a link at the end, you can actually get the web implementation. I'll show you what it looks like. And you have your own geocoding server. So here it is. So nominatum.openstreetmap.org. Yeah. As you can see, this is what sort of prompted us to run it locally. And there we are. And there's my home. And what's that? Yeah, I don't know. I'll have to ask my wife. I'll talk a little bit about spatial metadata. There's a big initiative or a big push to actually share what maps people have. So at the moment it's really hard to know what's out there. Really hard, like a lot harder than it should be. So OGC have come up with a standard called Client Services for the Web, CSW, and it allows people to store ANSLIC. ANSLIC is another one of those sort of standards. It's an Australian metadata standard for spatial data. ANSLIC compliant metadata for spatial information. So a lot of government agencies in Australia are running GeoNetwork instances to share metadata related to their spatial layers. But as a part of that ANSLIC standard, there'll be a link to the via OGC or WMS to the actual data. So you'll be able to find what maps are out there. So there was an initiative a little while ago called mymaps.gov.au where everyone was feeding. So GeoNetworks it's like a distributed sort of system where people can share information between GeoNetwork instances. So mymaps.gov.au is a centralised node where people would publish their metadata to. So I thought it'd be worth just throwing it out there, that there is a standard for geospatial, an open standard for geospatial metadata interchange. Okay, I've got about 15 minutes left. I was going to do 2 demonstrations, so you've got a choice. One is a quick demonstration of taking a shapefile, loading it up in uDig, inserting it into PostGIS, converting it into a SQL statement, creating a layer in GeoServer connected to PostGIS, publishing that, and then using openlayers. Or I could talk about spatial.ala.org.au, which is the project that I've been involved with, which is a biodiversity project which overlays species information and environmental data and mashes it all up and allows you to do analysis. You can do prediction analysis, you can do scatter plots, and it's designed for scientists really, but, and I'm not a scientist, but you might find that more interesting. So 1 or 2, hands up for 1. Hands up for 2. All right, two's the winner. Now, I'm not sure what our web connection's like, so I'm sort of relying on the wireless gods. So, but I'll have a crack at it. If this turns out to be unusable, I've got a series of screenshots that I'll go through and I'll explain it that way. But I'd highly encourage you to sign in and actually have a play with it yourself. So this is the URL here. You could go through ala.org.au, but it puts a whole heap of sort of crud around it. So if you want a nicer looking view, it's complicated enough as it is. So I'd probably recommend just going to it directly. So I'll load that up. Now this application, it's written in a framework called Java ZK. This sort of predates the current project team because the code base was inherited from IMOS, which is a CSIRO marine collection sort of portal. So it's another web portal. So we sort of reuse that code. It's actually an open source project. It's on Google Code. So if you look for ALA Spatial Portal on Google Code, you should come across it. We don't have many external contributors, but it's released under the Mozilla public license. So if there is interest out there to further develop it, or at least take ideas from it, feel free. It uses openlayers, so the same stuff that we're looking at before. All of the stuff in that right panel is openlayers. And yeah, there are 3 types of data that we can overlay on the map: species, areas, and layers. Species hook into our species occurrence repository, so a whole heap of museums, herbaria, universities, and government agencies have submitted species occurrence data. So if a wombat has been seen and identified as the southern hairy-nosed wombat, the latitude and longitude is recorded with a species occurrence. So we've got 20 million of these occurrence records across the country, covering animals, plants, birds, fish, everything. It's life. So so what I'll do is I'll just put in the Macropus rufus. So you can use scientific name or common name. Macropus rufus is the red kangaroo. So we can see there were 34,000 records being mapped. Small caveat, this isn't actually talking to GeoServer, this is talking to a Cassandra database with a Solar Index. So it's like a bit of custom stuff that we have, but it does use WMS. So the protocol that our custom spatial services use, we call it the biocache, it actually talks an OGC compliant protocol. So you could take an OpenLayers application and hook it into the biocache and render species information, for example. So we can see there it was, that was 30,000 points plotted straight like that, and we can select a record, and that'll give you information about that specific species occurrence out of the biocache. And if we go to view details, this goes into another part of the Atlas of Living Australia, and we'll see information about who actually collected that occurrence information, when it was collected. I'll just jump back, because that one might be a little bit slow as well. On the left here, we can see a few things. We've created a new layer on the left. We've got the layer name. We can switch between a density grid or point-based view. So if we select density grid, we can see it displayed in a different format. We can do other actions. So these are called hints down here. So these are things that you can do with it. You can actually download all the records in a CSV format and do your own data analysis on it. Generate a prediction. So given that species and some environmental conditions, so you can say heat and humidity, where could this species occur? And it'll actually overlay another layer on the map, and you can actually see where that species occurs. Let's add an environmental layer. We'll go for a climate layer. I'm just picking one at random. Okay, so this is evaporation annual mean overlaid on the map. Now that is coming out of GeoServer. That's a GeoTIFF file that's stored within our GeoServer instance. We can actually see what the exact value is by using a hover tool here. And if I hover that over the map, we can see and move that around, and we can get what the actual value is there. We've got our own spatial service that returns that information. And I think it also supports an on-click event as well. Say we wanted to find out what species occur in a region near me. So say I want to find stuff in my local nature reserve. I'll zoom in a little bit. And we can disable layers as well. So if you click that, it'll talk to open layers and just disable it. So, and if we want to, Canberra. One thing I'm really hooked on with open layers is the shift drag sort of feature. So you actually define a bounding box for the portal by holding down the shift key, and you drag it, and it goes to that particular point. I'm just going to go to Jerrabomberra because that's where I live, and we'll have a look and see what species have been observed in the Jerrabomberra Mountain Reserve here. What was that? Geospatial bogans.
What's the Latin name?
Okay, so what I'm doing here is I'm defining a rough polygon around this nature park. Very rough one. And do that. Okay. I know red's a really bad colour to use from a UI perspective. It looks like an error, but that's actually valid WKT. So it was one of those standards that we were talking about before. So I could actually cut and paste that, put it into an insert statement into PostGIS, so you can store it into a spatial table. Okay. So I've got an area now called My Area, and again it's created a new layer which I can disable and enable. And I can see here that these are all the things that I can do with that. I could download a species list for that area, so we'll do that. So there are two things, a species list and also all records. So records is associated with the actual occurrence records. Species is more of an aggregated view. It'll have the species name and account associated with it. So apply to an area, it's aware of all the areas that I've created in this session. So I'm just going to do it to my area. Grab a coffee. Here we go. Here's a preview of that species list. So we can see here family, scientific name, common names. So a species can actually have multiple common names, which makes things interesting. Life science identifier. This is like a unique identifier for a species, which is used quite extensively in the ecological biodiversity community. So yeah, and then you can click download, and that'll download a CSV file, and so you'll have all that information. So when you're out in the nature park with your kids, you can have a checklist of things to look out for.
This is a little bit orthogonal to the geographical side, Gavin, but if you actually identify flora or fauna that's not listed, how would you
contribute it? That's a good question. There's another project within the Atlas called Citizen Science. I don't know a lot about it. Do you know much about it, Gary? The Citizen Science project?
From the online form, you can create sort of observations and contribute back.
Also, if you take photos, you tag it with the Encyclopedia of Life. There's actually a process on the Atlas site. If you've got photographs that you want to contribute to this, you can actually get them into the biocache. And yeah, so
they're very, very, very hungry for the contributors.
It's not to the right there, so
and also, what I can do is add to map species, and I can just go all species and okay. And this will actually plot all of the species within that polygon, within my area. And what we'll do is we'll just get rid of that. And we can then facet based on an attribute. So we could go based on scientific name. There aren't too many records here by the looks of things. Yeah, there's only a handful really. But we can see here that it's colorized based on the actual scientific name of the species. And then you can subset that. So say I'm only interested in that one there, I can go create a layer based on that species, and that's now created a facet on that species.
Hey, Gavin, can you show off your Google Refine capacity? That's very cool.
Google Refine. You mean the scatter plot?
Yes.
Yep, okay. Have we got time? 5 minutes? Yeah. Okay, what I'll do is, it's starting to get a bit messy now, so I'll just reset my map. So resetting the map will just clear all your layers and just return you back to a known state. So if you get scared, that's a good one to know. Just, it's still a work in progress. So things like state, like session state, and login, so that you can't really save things for later on at the moment. So it's very much limited to your session. But the boys are working on that. So okay. So we're going to do a scatter plot. So I mentioned that we had a series of analysis tools associated with this. So I just mentioned some basic overlays, say species, environmental layers, and areas. And but there's also a ton of analysis sort of stuff as well. Prediction uses a scientific process called maximum entropy to find to create a prediction model based on environmental conditions and species distribution. You can find out where a species could exist, and you'll get a heat map overlaid on the map. I encourage you to have a crack at that. Scatterplot is the one that Gary's talking about. This is actually quite exciting because it actually, what I'll do is I'll quickly run through this, and I won't explain every step because there's a lot to it, and I'm not really a scientist, but I can give you a rough idea of what it's doing, and you can probably work it out from there. So we'll go with the kangaroo again. Now this calls out to another web service to do the species autocomplete, so that's why there was a bit of a delay there. That's quite a new thing. We used to have our own index of species data, but now we're a lot more tightly integrated with the biocache, which is good. So I'll go next. So now what we're doing is we're selecting X, Y environmental. We're going to select two environmental layers that we want to see. We want to see a relationship between the two of those. So I'll go with Y1, temperature, and 12. So I'm going to have temperature and precipitation as the two axes. No background species. And you give it a name, and that's just going to be the layer name that you see on the left-hand side. Process. I did. Yeah. So what we'll see on the right-hand side, we should see the species observations plotted on the map. And on the left-hand side, we'll see a histogram, which we see down here. It looks better on a bigger screen, but you'll get the idea. The histogram shows the species occurrences in relation to those two environmental conditions, precipitation and temperature. And if we select a few points within that histogram, give it a moment. We can see them highlighted in the physical world in red. So all of the points in here that have that precipitation, that temperature, these could be outliers because you can tell by the histogram that we've got some outliers here. We've selected them and we can narrow down on it over here. So this has for ecologists, this is gold. You know, they love this kind of stuff. So open source, open data, geospatial. The end.